Hello and welcome to another one of these ADD videos. Today we're going to be discussing substitution and elimination reactions. When people are looking at substitution and elimination reactions, they focus so much on the details they get lost and they fail to see the big picture. I feel like if you take a step back and see the big picture, the individual problems become a lot easier. The substitution reaction, what we're going to have is an electron-rich species. Actually, both we're going to have electron-rich species, but it depends what they do. If they attack an electron poor carbon, an electrophile, and replaces a leaving group, then it's a nucleophile. So here we have a carbon and a halogen. This is an alkyl halide. We discussed how to make these with free radicals in the previous chapter. Now, these guys are going to be attracted, these electrons, to this carbon, because this carbon is bonded to a halogen. And the halogen has a high electronegativity, so it withdraws the electrons, making this partially negative, this is partially positive via the dipole, and this is electrophilic, likes electrons. Nucleophiles got electrons. So it comes and binds, and either in a two-step process or a one-step process, we end up replacing that halogen leaving group with a nucleophile. What makes a good leaving group? It has to be electron withdrawing, it has to be stable when it leaves as an ion. Elimination reaction is a little different. Our electron-rich compound could be the same exact compound as we had over here, okay? But instead of attacking this electron-poor carbon, what's going to happen is we're going to attack a hydrogen adjacent to it, all right? E2, it has to be anticoplanar, we'll discuss that later, but E1 can be this one here. And we end up basically having the base come in, attack the hydrogen, leave the electrons behind, and form a double bond. They fill the p orbital and form a pi bond. You get an alkene, all right? You can further make distinctions between substitution and elimination depending on one or two. So group one, for instance, you're going to be looking for weak to moderate attackers, alcohols, okay? It's a two-step reaction. First step is we're going to form what's called a carbocation. If you remember discussing these are the ones that have the NTP orbital, they're sp3 hybridized, and basically have a plus charge, 3-2-1 stability. Then we're going to either have elimination if we attack the hydrogen with our electron-rich species, or if it's attacking the electrophilic carbon here, then it's a nucleophile, and it's a substitution reaction. So the one reactions are solvolysis reactions. What does it mean to be a solvolysis reaction? It means that the solvent is what's doing all of the work. And we place a solute in the solvent, right? And the solute usually is far smaller in concentration than solvent, and the concentration is so drastic that it's irrelevant. Solvent's concentration is irrelevant. Just a solute being the alkyl halide. So the kinetics as a result is just based on the concentration of the alkyl halide we're given. Hence the one reactions, E1, SN1. All right, so let's focus on SN1 reactions specifically. Here we're going to have a one reaction, so we need a weak or moderate attacker. And we're going to have a carbocation that forms first. Remember, the one reactions are two-step reactions. And then substitution or elimination will occur. So here's an example. We have an alkyl halide, right? So a carbon chain bonded to a halogen, and it's an alcohol solvent. All right, remember the one reactions are solvolysis reactions, so the solvent does all the work. And that's why it's a one reaction, it's unimolecular. The solvent always is in much greater concentration than the alkyl halide. So the rate and the kinetics of the reaction only depend on the alkyl halide concentration. So when you put that in here, what happens is it ends up getting you a heterolytic cleavage in which the halogen gets the electrons, this bond here, and carbocation gets none of them. So it's got an empty p orbital, making it very strongly electrophilic. It wants electrons. So from here, what happens is the solvent is going to act as a nucleophile, so this alcohol is going to come and use its oxygen lone pair electrons to form a bond with the empty p orbital in the carbocation. Whenever the solvent molecule comes and uses its lone pair electrons to fuse to the carbocation, you end up with this scenario in which you have a positively charged oxygen. There's two lone pairs. Remember here, we've got four lone pair electrons, 2 and 2. And two of them form the bond with the carbon here, the carbocation. And there's two left in the structure not drawn. So we'd have a valence of 6 if we were to do the formal charge for oxygen, 6 minus 1, 2, 3 bonds, and then the two lone pairs we don't see gives us 6 minus 5, which is a +1 charge. Oxygen does not like having a plus charge. It's perfectly happy with a minus charge, but plus not too happy with. So what happens is the solvent comes and picks up this hydrogen here and leaves you with an ether. So essentially what happens, this R is part of the nucleophile, is we get the RC we had originally, and instead of the halogen, we have the nucleophile attached to the electrophilic carbon. And then we have a protonated alcohol, whatever the alcohol is, ethanol, methanol. Solvents are typically weak or moderate, like water or alcohols. We want the solvents to be polar, so they can stabilize the ionic intermediates that occur, the carbocation. All right, all these charges going on here, so we want it polar. And also, we need them to be soluble. So what we do is we use a protic solvent so they can solvate the ions, especially the leaving group, and stabilize it as it leaves. A stable leaving group ensures the formation of the carbocation. So halogens are typically used. You might say tosylate or mesylate, but something that's not going to be a strong base when it leaves. Although you see both elimination and substitution products in the one reactions, it's possible to see that you're going to favor one over the other. Right? So if I put an alkyl halide in an alcohol solution, I'll form a carbocation, and I might get some rearrangements, whether it's a methyl or hydride shift, but I'm going to see most of the time the elimination product and this substitution product that we just had. So how can I favor one over the other? One way to do it is by using heat. Heat will favor elimination reactions, lowering the activation energy of that elimination reaction, binding with the hydrogen. Or you could use silver nitrate. Silver nitrate will push the reaction towards the substitution. If you want to push the direction one way or the other, you can use either one of these techniques in elimination. All right? We'll go over E1 reactions in the next video, so make sure you check out those series. But this is SN1. Hope I've clarified things enough for you to try some problems. Again, the key as always is to practice as many of these as you can, and it'll become second nature. Thanks for watching as always. Have a great day.